Hi, I'm Steve Buckland, and this is the Point Transit Sampling Lecture. In point transit sampling, you have points spread through the survey region, usually according to a systematic design evenly spaced through the area, as is shown in this diagram. But sometimes it can be a randomized design with points located purely at random within the region or within strata in the region. If you detected all animals within a distance w of each point, then you've just got a plot sampling method. And for that, all you need to do is total up the number of animals you record and divide by the total area counted. And the area counted for each point, if the radius of the area covered is w, the area counted is pi w squared. And so if there are k points, we'll have counted an area of k pi w squared in total. So estimated density is then just the ratio of the numbers counted over the area counted. In practice, you're not able to detect all animals within a distance w of a point. So you have to deal with uncertain detection. In that case, the effective area surveyed is smaller than the area of the plot. The area of the plot is a circle of radius w about the point. And so the total area is pi w squared for each point, but the effective area is smaller. The rho here is an effective radius, the nu is the effective area. So the area covered, pi w squared for each point times k. But we don't detect everything within that area, and the proportion detected we can express as the effective area divided by the total area. And that comes down to a ratio of the squared effective radius to the squared actual radius. And then the estimated density is the numbers counted over the area counted, which is k pi w squared, and then adjusted for uncertain detection. So, for example, if we estimated that on average we detected half the animals on a plot, we'd double our density estimate to take account of the half we didn't detect. And so what we end up with is estimating density from the numbers counted divided not by the total area surveyed, but by the effective area surveyed. Pi rho hat squared for each point times k for the number of points. The area covered around a point increases with distance. So if you look at an area within one distance unit of the point, that has an area of pi r squared, and r is 1. If you look at the area within 2 of the point, that has area 4 pi times 2 squared. So the area between 1 and 2 meters is the area of the circle of radius 2 minus the area of the inner circle. And so that leaves us with 4 pi minus pi, or 3 pi. And then if we look at a radius of 3, the area of that circle is 9 pi minus the area of the rings inside, 3 pi and pi, leaves us with 5 pi for this third ring, and 7 pi, and so on. And you can see the area of these rings increases linearly. That means the number of animals available for detection on average, will increase linearly. So there'll be more animals available for detection at larger distances. To offset that, the larger the distance, the less likely you are to detect an animal. So you end up with observations that increase with distance up to some maximum and then fall away again. And if we were detecting everything out to distance w, you'd get a straight line where this dashed line is, and the histogram, the bars would get progressively higher, roughly linearly. So we see we're detecting everything out to here, and then we start to miss animals. And then we miss more and more of them until the observed proportions, the observed numbers detected, declines. So the histogram rises to a maximum and falls away, but with some random fluctuation about that. If we rescale our histogram bars to take account of the increasing area with distance, then we can show how our detection function fits our data. So in this case, in the first interval, we had very few detections because there's a very small area within that distance of the point. Then when we rescale, that histogram bar gets much bigger because we rescale by dividing by the midpoint of the distance, and that's a small value here. By contrast, if we look at the last interval, it's very low in this scaled histogram because we've divided by a large distance, whereas in the previous histogram it was a lot higher. So this histogram shows us the numbers detected by distance, which means that this histogram can be a little misleading because the number of observations in here where the bars are highest are actually quite small, and numbers of observations out here where the bars have started to shrink are actually larger when you look at the original histogram of the probability density function. So for line transit sampling, you don't get that effect because the availability of animals with distance from the line, when lines are randomly placed, is uniform. There's many animals on average at each distance. And for this plot, we've taken the truncation distance, the half width of the strip, to be 100. The detection function then acts as a filter of observations from this uniform. And so the resulting observations have the same shape to them. We see everything at or close to the line, but progressively as we get further from the line we miss more, and so we see fewer animals. Now, point transit sampling differs because the availability of animals increases linearly with distance. And so we still filter that through the detection function, but now numbers detected by distance increase initially, and only when detection probability gets quite small does it get to a maximum and turn around and decline again. Essentially, the product of the top and the middle curves gives us something that looks like the bottom curve, and that's what our histogram of detections will tend to look like, with some fluctuation, of course. Now, the effective radius is the distance from the point, such that you see as many animals beyond rho as you miss within rho. And so this curve is the probability density function. It has an area of 1, as all probability density functions do. And you can see that the two shaded areas have the same size because they correspond to the same number of animals, And so this triangle will have area 1 also. And we can exploit that to get a relationship between the effective radius and the probability density function. So the function has an area under the curve of 1. The area of the triangle is the base, which is the effective radius rho, times the height, which is rho times the slope of this dashed line, which is the tangent to the probability density function at distance 0. And so the area of the triangle is the product of the base times the height times 1/2. And so if we denote the slope of that dashed line by h of 0, then we can express the area of the triangle as rho squared times h of 0 divided by 2. But we know that triangle has area 1 because it has the same area as the area under this curve, because the two shaded areas are the same size. And the shaded curve is a probability density function which must satisfy that result. So that allows us to set the area of the triangle to 1, and that allows us to get an expression for the effective radius as a function of the fitted probability density function. And because statisticians have lots of tools for fitting probability density functions, that gives us the tools to estimate the effective radius. And the effective area will be just the effective radius squared times pi. And therefore we can estimate density as the number of animals divided by the area counted times estimated probability of detection, and when we plug the values in, that gives us this expression: estimated density of animals, number of animals detected, times our estimate of the slope of the PDF at distance 0 divided by 2 pi k. Okay, that gives the underlying methods for point transit sampling, and I'll finish this lecture just by summarizing the notation we use, which will be used in later lectures. So known constants and data. K is the number of points surveyed in the design. N is the number of animals detected, or if your animals occur in groups or clusters, it's the number of groups detected. Ri is the distance of the ith detected animal from the point. W is the truncation distance for distances from the point, the maximum distance at which you record them. Capital A is the size of the survey region. Small a is the size of the region you count, the circles of radius w. With k circles, there'll be an area of k pi w squared that you count. And if you have animals occurring in clusters, then we'll also record the size of the ith detected cluster for each of the n detections. The functions that we're interested in, first of all, the detection function, the probability that an animal at distance r from a point is detected. The probability density function, and that reflects the relative frequency of distances recorded when you detect animals. And for line transit sampling, those two functions were the same shape. Here, they're not. And then h of r is the differential of the probability density function with respect to r, which mathematicians would denote f prime of r. and it's the slope of the probability density function, the first derivative. And it's only the value of that derivative at 0 that we're interested in. Parameters. D is the density of animals per unit area. D sub S, that's for if animals occur in clusters. That would be the density of clusters in the area. Population size is density times area of the survey region. Rho is the effective radius. Nu, the effective area per point, which is pi rho squared. And P sub A is the probability of detection of an animal or cluster in the covered area A. Okay, that's covered the basics of point transit sampling, and the next lecture will address case studies illustrating the use of the methods. Thank you.